Well, thank you very much. I would like to thank the organizers for the invitation. It's my first time at the Royal Society, so it's quite impressive to be here. And so this is what I'm going to talk about. So I'm going to restrict the framework. So I was told to use the cursor rather than the pointer. I'm going to restrict the framework to Ricci flat backgrounds, so the conformal boundary is null, and massless fields. Because I'm going to talk partly about conformal scattering. And so the general purpose of scattering theory, whichever approach you choose to use, is to understand the asymptotic behavior of fields. And, but not just that. So you want to then prove that the knowledge of the field is equivalent to the information contained in their asymptotic behavior. So in a sense, from the field you can extract the asymptotic behavior, but once you fix the asymptotic behavior, you can also extract a field. The two informations are equivalent. And once you've done that, so you've got your complete scattering theory, then you can construct your scattering operator, which is an isomorphism that is going to bypass the whole evolution. It's a summary of the evolution of the field, and it's going to associate to the past asymptotic behavior the future asymptotic behavior. Okay? I'm going to talk about essentially two approaches to scattering theory: conformal scattering theory and spectral analytic time-dependent scattering. I'll also mention Lax-Phillips theory, which is another type of analytic description, but quite different from the spectral time-dependent approach. So in terms of history, conformal scattering started with a beautiful paper by Roger Penrose in 1965, I think, in the Proceedings of the Royal Society, about zero S-mass fields and their asymptotic behavior. And he proposed the idea of conformal scattering, essentially. So the idea was really born with the conformal method. And Roger Penrose proposed the idea of setting up initial data on scri-, evolving them, and then obtaining restrictions of the solutions on scri+. It's not exactly a scattering theory formulated like this. You would need to understand the fact that you can go back always without losing any regularity or information, that somehow the process is reversible. But the idea was essentially there. And then there's the Lax-Phillips theory in '67, which is contained in a book called Scattering Theory. And Friedlander in 1980 constructed the first actual conformal scattering theory by putting the two things together. So he used the conformal method to recover the Lax-Phillips theory in a particular static framework that is genuinely curved, but not a solution of the Einstein equation. If you impose the Einstein equation on top of that, then you get flat spacetime. And then Baez, Siegel, and Zhu extended the theory still to static frameworks in the 1990s, but for nonlinear equations. So Lionel Mason and myself in 2004, we wrote a paper constructing a conformal scattering theory using a slightly different method based on energy estimates. And this is on generically time-dependent frameworks that are asymptotically simple, with a smooth time like infinity. And then the theory was extended by quite a lot of people, shown here in chronological order, including one of the organizers. And as for the spectral approach, it started in 1982 with a paper by Dimmock and Kay that constructed a scattering theory for the wave equation on the Schwarzschild spacetime. Then Alain Bachelot and his students did a systematic study of the spherically symmetric case in the 1990s. Things were then extended using different techniques to the Kerr framework. Again in chronological order by Dietrich Heffner and Dietrich and myself and Thierry Daudet in essentially the early 2000s. Again, things got extended by quite a lot of people to more complicated situations, generalize. So Dietrich and Vladimir Georgescu, Christian Gérard, Nicolas Besset, there's Mogdad as well, whom I forgot, I'm sorry about that. And but I forget also a lot of other people. So I'm going to try and describe to you the essential principles of the two approaches. So first of all, analytic time-dependent scattering. So let's start with a very general abstract description of the theory. So you consider two self-adjoint operators that are not necessarily bounded on two different Hilbert spaces. And the Hilbert spaces could be the same, but in general, what will happen is that you will have different Hilbert spaces. And you consider the Schrödinger equations associated with each of these operators and the corresponding propagator. So this is, let's call it the complete equation, or the physical equation. That's the equation you want to study. So you've got the Hamiltonian operator H. This is the propagator. It's a unitary propagator, given the assumptions I've made. And it's the thing that to the initial data associates the solution at time t. And this lives, the solutions at any given time live on a given Hilbert space that I will call the finite energy space. Now, this is meant to be a simpler equation in general, and I'm going to call it the comparison equation. H0 might be the comparison dynamics or a simplified dynamics. And essentially, you have a similar framework on a Hilbert space that usually might be different. So if the two spaces are different, sorry, what you need is some type of identification operator that from functions in H0 will associate functions in H with as little modification as possible. So in some cases, it could be something that cuts off a part of your domain. So you could have functions living on the real line and you cut off half a real line. So if functions are supported on the positive real line, then it essentially doesn't do anything to those functions. This sort of thing. The norm in good cases should be 1. And then you will try to compare the two dynamics by defining the so-called wave operators. So you have direct and inverse wave operators. And they are defined as follows. So what you do, you start so for the direct wave operators, you start with initial data for the simplified equation. And you apply the forward propagator for the simplified equation from time 0 to time t. Then you use your identification operator to go to the other Hilbert space. And then you use the backward propagator for the complete dynamics down to time 0. You do that for any given t. You take the limit as t goes to infinity, and you hope that it converges. Strong limit is like a pointwise limit for a function. So it means that you take a limit for any data in H0. The inverse wave operators are just the other way around. You start with data in the full Hilbert space rather than the simplified one. I mean, the Hilbert spaces are not necessarily simpler. Right. So, and the idea is then that if in some sense you can understand H and H0 as being asymptotically close, whatever that might mean, it depends on the situation, then you will have this sort of result. So the wave operators, direct and inverse, will exist. With the assumptions I gave, they would be isometries, and the inverse wave operators would actually be the inverse of the direct ones, and also their adjoint. So the important objects that you're going to deal with in your interpretation of your scattering theory for the full equation are, first of all, the initial data, the corresponding solution here, and these objects that are the images under the inverse wave operators of the initial data. So these are called the scattering data, future and past scattering data. So they describe the asymptotic behaviors, if you like, in the future and the past. So by construction, if you have that these wave operators exist, you will have this property. So you start with the scattering data as initial data for the simplified dynamics. You look at the corresponding solution. Of course, you need to use your identification operator for all the quantities to be in H. And you compare that with the physical solution. And as time tends to infinity, they will approach one another. So the fact that the wave operators exist is telling you that you're describing the asymptotic behavior of the physical solution as being similar to a solution to the simplified equation. Then you can construct your scattering operator. So it's the thing that to the past scattering data associates the future scattering data. And you define it as the direct past wave operator is composed of the inverse future wave operator. So let's try and describe a bit more precisely some features on a given example, and that's scalar fields on Schwarzschild spacetime. So this is the Penrose diagram of the exterior of the black hole. So we work outside the horizon in the domain of outer communication in using the Reggie-Wheeler coordinate. So this is quite important, actually, even though it's just a simple choice of coordinates. This is the horizon-defining function, and we look at the wave equation on the Schwarzschild spacetime. So that equation contains a first-order derivative in R with a term that decays, that's a long-range term, some power of some 1 over R times d over dr. So it looks, long-range terms are annoying in scattering theory. You usually want to get rid of them if you can. If you can't, it means you have to modify your theory and the wave operators get more complicated and the interpretation is more complicated. Here, there's a simple thing that you can do. You multiply your unknown by R and miraculously the term disappears. It's exactly what happens in flat spacetime for the wave equation. You've got the 2 over R d over dr term in spherical coordinates. It disappears when you multiply your unknown by R. Okay? So this is the equation you get. These are all short-range things. They decay at infinity like 1 over R squared or 1 over R cubed. The corresponding Hamiltonian is this operator, H. And you have to consider that you have 2 asymptotic regions. So you have infinity and you have the horizon. So this is why, in a sense, the R star variable is handy. But essentially, you're doing a scattering theory for the point of view of a static observer outside the black hole. And to such an observer, the horizon is an asymptotic region. So then you want to choose your comparison dynamics. At the horizon, there's essentially not much choice. I mean, there's only one natural choice because you have a fast decay in terms of the R star variable. So the function f decays exponentially fast in R star at the horizon. So a very natural thing to take is removing from H all the terms where you have f. Well, these are not bounded, but we're going to ignore that. You can control this in the propagators, actually. Or you can do decomposition in spherical harmonics if you like. It's only hiding the problem. But this is really not a problem. So this is the sort of comparison dynamics you're going to consider, and it's the Hamiltonian for the 1 plus 1d wave equation. Okay. So you've forgotten about what happens on the 2-sphere. At infinity, then the decay, of course, of the function f is different. It doesn't decay, it tends to 1, and it approaches 1 not exponentially fast. So you have 2 reasonable choices. You can either take the same comparison dynamics, or you can choose the Hamiltonian for the wave equation on Minkowski spacetime. So this, by doing that, you will understand waves on Schwarzschild as behaving like waves on flat spacetime at infinity. Okay. Notice that there is something a bit odd in this Hamiltonian. The radial variable of Minkowski spacetime is R star and not R. Okay. So this choice means that what you're doing here is you're trying to glue Minkowski spacetime on Schwarzschild spacetime near infinity, and you're stretching it in a manner that will guarantee that the radial propagation speeds are the same on the 2 spacetimes. So by doing that, you're avoiding artificial long-range artifacts. Or artificial, long-range perturbations. So if you don't do that, you can still construct a scattering theory, and some people have done it, but it's less natural, more complicated, and it makes less sense. So you have 2 different function spaces for the scattering data, depending on the type of comparison dynamics that you're going to choose. So for H1, for the wave equation, you get the energy space for the wave equation on Minkowski spacetime. So this is a homogeneous Sobolev space of first order cross L2. This H1 dot is simply this, you can understand it as the set of functions, if you like, whose gradient is square integrable in R3. Okay? But you have no explicit control on the integral of the square of the function itself, only the gradient. For H0, it's a weaker control, so it's homogeneous Sobolev space, but purely in R, with values in L2 of the sphere. So you have no control whatsoever on the angular derivatives. Okay? So you see that the choice of comparison dynamics impacts quite strongly the control you have on the scattering data. Right, and then you define the wave operator. So of course, the fact that you have two asymptotic regions appears in the definition of the wave operators. So the direct ones are going to be, in fact, two operators. One, well, four, in fact. But in the future, you have two operators. One at the horizon, one at infinity, and the same in the past. And for the reverse, or the inverse wave operators, then there will be a sum, because you have to put together the contributions coming from the horizon and from infinity. The essential tool that one uses to prove the existence of these wave operators is called Cook's method. It's based on a very simple argument that a function has a limit, that if you can guarantee that you have a function on R, okay? And if you can guarantee that its derivative is integrable at infinity, then you know it has a limit at infinity. So it's not a necessary and sufficient condition, it's a sufficient condition for the existence of wave operators. So you take some data in your energy space, and you look at the derivative. So this is shown, as I say here, for direct wave operators at infinity. So you look at this. J is either 0 or 1, of course. So you take this quantity that is, whose limit you want to study to define your wave operators. You take its time derivative. So you get that. Okay, this is the time derivative of the quantity here. And you say that if that thing is in L1, if it's integrable in time, then you know that the corresponding limit exists. If you can prove that for any element of your energy space, you've got your wave operators. And if you can control your identification operators, you have a bounded operator everywhere. It's not always the case. In fact, usually it's not the case that you can prove that limit for any element of H. Usually you work with a dense subspace. Then, if you can have a uniform control of these norms, the wave operators can be extended uniquely, and also the strong limit property is valid for the whole energy space. There are some slightly more pathological cases in which the strong limit doesn't survive on the whole energy space, and it's only valid on a dense subspace. So it's a case-by-case study to see what you really have and how you want to interpret it. But then the question is, how do you apply Cook's method? So the idea is that these two operators, so you can sort of ignore the identification operators. In good cases, it's going to be fairly neutral. And what you really see here is the comparison, the difference of the two Hamiltonians. The idea is that as you approach the asymptotic region, these are going to be close. So, for instance, going back to their definition, this is going to be close to that at infinity, and the difference is decaying like 1 over r squared. So it's integrable in one space dimension. And at the horizon, things decay exponentially fast, so you have a similar behavior. So how do you understand that the solution somehow goes into the asymptotic region? Okay, so you need to make sure that on a compact domain, the energy tends to 0. So you prove local decay. It means that the solution really moves away from any compact set, goes into the asymptotic region where you can compare the two operators. So you need to prove some local decay result. The strongest possible version of that is the Huygens principle. So it's telling you not only that, so you start with compactly supported data, then you know that the solution is going to become 0 on any compact domain for large enough time, but you know more than that. You know that the size of the domain in which the solution will be 0 will increase at speed 1, okay? So when you know that the difference of these two operators decays like 1 over r squared, it's going to tell you that this quantity decays like 1 over t squared, because the solution becomes 0 in a domain that grows with speed 1, okay? So it guarantees this integrability in time. But of course, the Huygens principle is rarely valid. So here, it's a nice case. It's valid for actually all comparison dynamics, well, in a certain sense, in one dimension. If you choose your data, if you represent your data properly as the incoming or outgoing ones, then it is valid. Generally, you don't have a Huygens principle, so you're looking for weaker versions of the Huygens principle. So if you're in spherical symmetry, you can separate variables. People usually do things called trace class perturbation techniques. So they're quite easy to use, but not very flexible. Something that's much more flexible, but more technical to obtain is a so-called minimal velocity estimate. So it's something that comes out of Moore theory, which is a spectral version of time-dependent, well, it's a spectral analytic tool to study the singular continuous spectrum, really, of an operator, but it's very useful in time-dependent scattering theory. And you're going to prove a result like this for any epsilon strictly lower than 1. So you take some data in your energy space and consider the associated solution. Then usually in Moore theory, you need to do cutoffs in energy. So this is a chi of h here. So you localize things in energy. You need to be able to localize anywhere. And then you only consider the part of the solution that propagates at speeds strictly lower than epsilon. So you cut things off in a narrow cone, if you like, locally. Then you take the energy norm of that, and you multiply by the measure with density 1 over t. So that decays already, but not enough to guarantee integrability. The fact that this is finite, so this is the minimal velocity estimate, the fact that this is finite will tell you that this norm is adding a little bit of decay, just enough to make the thing integrable. So it's telling you that in some weak sense, this is tending to 0. So it's a weaker version of the Huygens principle. Okay. And so this is essentially the features I wanted to show you on the analytic scattering theory. The way I've described it, it really looks like this sort of thing is valid in a stationary framework only, or static even. I mean, the operators don't depend on time. It's not completely true, but you need a good control on decay, and you need uniform estimates. But you can, these techniques can be applied in time-dependent frameworks, and there was something we did with Mogdad in a time-dependent framework, Mogdad and Dietrich. So there's no principle against time-dependent settings. So conformal scattering. So that's a very different approach. That's a much more geometrical approach. So you start with a physical, we call it physical spacetime. You have the spacetime on which you want to study an equation. And then you have another feature, which is a compactified spacetime, conformally compactified spacetime. And the relation between the two metrics is a conformal transformation. So the metric g hat is just multiplied by a positive function, a multiplication of g by a positive function, and that function tends to 0 at infinity, to bring back infinity to finite distance. And then we study the conformally invariant wave equation. So on your initial spacetime, this is the expression. And if phi is the solution of it, so phi could be anything, a distribution even, this is equivalent to saying that phi hat, that I will call the conformally rescaled field, so it's just phi divided by omega, satisfies the same equation on the rescaled spacetime. Okay? The conformal scattering construction only works with the rescaled spacetime, or the way we do it anyway. So you only work with this equation. Then a conformal scattering theory for the wave equation would be the following thing. You construct operators that I will call trace operators that to initial data for this equation, or that one, it's up to you, whether you want to use the physical initial data or the rescaled ones, doesn't really matter. To these data, it associates the restriction of the rescaled field at the conformal boundary. So the conformal boundary of the spacetime, again, I'm dealing with Ricci-flat situation, so it could be null infinities, it could have horizons, you could add some more asymptotic ends if you like. So the examples I'm going to show you, it's just Schwarzschild, so it's going to have scribe plus minus and h plus minus, and that's it. And you want to realize that these operators are well defined and that there are isomorphisms between well-chosen function spaces. So this, once you've done that, then you can construct your scattering operator, and you start from the data in the past at scribe minus and the past horizon. You transform them into data for an equation using the inverse of the past trace operator, and then you compose that with the future trace operator. So the essential thing to understand then is that the scattering theory is equivalent to proving that the Cauchy problem at the past at any conformal boundary, past to future, is well posed. Okay, because you start from data. They represent a solution in a one-to-one way. You associate the restrictions at the conformal boundary. You're saying that the two informations are equivalent. So you can associate the restrictions at the boundary to your solution, but then you can associate the solution to the restrictions at the boundary. It means you can solve the characteristic Cauchy problem or Gauss-Sat problem. Okay, so this is the same thing. And what you can do is you can use Holmander's way of proving that the Gauss-Sat problem is well posed. This is a short paper from 1990, and it's following the three simple steps there. So you start by defining your trace operators on a dense class of data. So you deal with smooth and compactly supported data on a Cauchy hypersurface. Okay. Then the fact that these admit that the corresponding rescaled solutions admit smooth restrictions at the conformal boundary is just a simple consequence of general theorems for hyperbolic equations on globally hyperbolic spacetimes by Leray. Then, so you have your trace operators, but only for smooth compactly supported data, which is really not what you want. Then you prove energy estimates both ways between a Cauchy hypersurface and your conformal boundary. So what does this do to you? Or for you? So you control the energies both ways, okay? So it means you control the energies of the restrictions at the conformal boundary by those of the initial data, but then conversely as well. So this allows you, so one estimate will allow you to extend your trace operators as bounded operators from two function spaces that really are defined as the completions of smooth compactly supported data in the energy norms you obtain. The other estimate will tell you that these operators will be one-to-one and they will have closed range. So it's telling you much more. Then the only thing you need to prove if you want to show that T plus minus are extended as isomorphism is the fact that they're surjective. Okay? But then surjectivity boils down to something a little simpler, which is the density of the range. And for this, you do it by hand. So you pick a dense subclass of data on the conformal boundary, and you construct solutions to the Gauss-Sat problem by hand, usually using a sequence of solutions. The way Holmander does that is by slowing down the propagation to make the conformal boundary, well, in this case, it's a finite null hypersurface, to make it space-like. And then he has weak convergence arguments. So you can do it this way. Once you've solved the Gauss-Sat problem, you've got your theory, your conformal theory, and then you can forget about the space-like slice and define your scattering operator that goes from the past conformal boundary to the future one. In principle, the construction is insensitive to time dependence, which doesn't mean it's as easy in the time-dependent case. So time dependence may be complicated enough to make it really hard, in particular when you want to obtain the energy estimates. So schematically, this is how things go. So you have the initial data, the Cauchy hypersurface, and the conformal boundary. Your trace operators go this way. So what you see is that the trace operators are the analogs of the inverse wave operators in the analytic theories, in the time-dependent scattering theories, okay? Because the inverse wave operators started from the physical data and associated the scattering data. So this is exactly what the trace operators do. So you've got a sort of opposite point of view in the conformal scattering approach to the time-dependent analytic approach. And strangely enough, also in the time-dependent analytic approach, usually the inverse wave operators are more difficult to construct because you don't have a Huygens principle in general. Whereas in the conformal scattering approach, the construction of the trace operators is, in a sense, easy. But it's in their extensions that you find the difficulty. So you have a sort of different localization of the difficulties. So a bit more details on the second step, the energy estimates. Okay, so you want to define an energy current. So you start by choosing, if it's not naturally imposed by the equation, a stress energy tensor So for instance, if you work with a conformal wave equation, so you have your wave equation and you have the scalar curvature, okay? And so you may choose the stress energy tensor for the wave equation on your spacetime or for the Klein-Gordon equation. The second one will give you control on the zero-order term containing the scalar curvature that the stress energy tensor for the wave equation will not do, okay? So it's a question of choice. In what remains, I will assume that I've chosen the stress energy tensor for the wave equation. Then you choose a time-like vector field, that's your observer, tau, and the energy current is just a contraction of the two. And you do your energy estimates using the divergence theorem. The choice of observer, well, it's the observer is a time-like vector field, future-oriented in the bulk of your space-time. You have two classes of natural choices that you can make. So you can choose tau so that it remains transverse, it remains time-like, if you like, at the null conformal boundary. So the energy space that you will get on the conformal boundary will be something like a full homogeneous H1 space on scry and the horizon. Or you can choose tau to degenerate and to become null at the conformal boundary. This will give you a weaker control without any control on the angular derivative. Okay, so you see the same function spaces that you got from the time-dependent scattering theory appearing here, but emerging from a different type of choice. This I would tend to consider as preferable. It's a weaker control and it's a more natural thing in a sense, but I suppose that's probably a matter of personal taste. And so you always have a full homogeneous H1 control on a Cauchy hype surface, but with different types of asymptotics depending on the choice you make for tau. So the strategy for proving the energy estimates. So you've got two types of difficulties that you can deal with. The first one is when you're working with spacetimes that are non-trivial, so you have they contain energy. It means their conformal structure at space-like infinity is singular. Okay, so how do you avoid the singularity at I0? Well, it's quite simple. We're dealing with hyperbolic equations, so they have finite propagation speed. So naively, if you start with compactly supported data, so they're supported away from I0, and the solution will propagate at finite speed, and the support of the solution will keep away from I0. So this allows you to perform your energy estimates, because you can, if you like, cut off a neighborhood of I0, replace it by something smooth, doesn't modify the solution, okay? Of course, if you can only do that, you have nothing. But then, if your estimates are uniform in your data, you can extend things by density, and you get estimates valid for any type of finite energy solution. So this is the method. When you try to come back and solve the Gauss-Seidel problem, things are more difficult. But you can essentially, again, use the finite propagation speed by a kind of... so you do a cutoff and smoothing technique, and you can use the same type of argument. If you work on a black hole spacetime, it's very different, because the singularity, you have an added singularity at I+, and no finite propagation speed result is going to prevent you from hitting I+ in the future. So what you do is you artificially cut it away. You keep away from I+ by adding this type of hyperboloid. So you prove your estimates in the past of a given hyperboloid and in the future of a Cauchy hypersurface. So it gets you a closed hypersurface on which you can prove your estimates. So the estimates need to be uniform, and then you want to push that hypersurface all the way up to time like infinity. And you want to show that the energy on it tends to zero as you approach I+. Okay? So this is a global decay result that you want to use in that case. So you can imagine that you have a point on a time-like curve, if you like. You look at the future of that point, and you want to show that maybe the energy on the conformal boundary contained in the future of that point tends to zero. Or you look at a hyperboloid supported on the boundary of the future of that point, and then you push it up, and you want to show that the energy tends to zero. Okay. So this is more technical things to prove. Let's try to sum up some similarities or differences between the two types of approaches. And again, I'll do that on the wave equation, for the wave equation on the Schwarzschild spacetime. So in the spectral approach, what you had was that wave operators were isometries. In the conformal picture, it's the trace operators that are going to be isometries on Schwarzschild spacetime. So you've got this similarity. Then you have, in the spectral case, a freedom of choice in the comparison dynamics, and this is reflected in the conformal picture in a freedom of choice for the observer. And we noticed that these two freedoms of choices give you actually similar, very similar settings in the function spaces for the asymptotic data. And then you have something quite different in that, in general, the scattering data live on a different space. They're not necessarily related to the space in which you look at your equation. Whereas in the conformal picture, the scattering data are geometrically localized at the conformal boundary. So that really is quite different. Something that's really important to notice also is that in the Schwarzschild picture, if you choose H0 as a comparison dynamic, so H0 was the Hamiltonian for the 1 plus 1D wave equation, okay? So the propagator is essentially the principal null geodesic flow, right? So it means you restrict to outgoing data for the 1 plus 1D wave equation, and the propagator, what it does is just push you along the radial null geodesics, the outgoing ones, and take ingoing data, it pushes you along the ingoing radial null geodesics that are also called principal null geodesics, because the directions are the roots of the Weil tensor on the Schwarzschild spacetime. So this is an important feature. And what does this mean? Well, it means that the scattering data at Scri plus really are the radiation fields. So what I mean by the scattering data here is the scattering data in the time-dependent picture. So they are solutions to these equations corresponding to H0, so they're propagated along this principal null geodesic flow. And it means that they can be identified as functions on Scri. So they really are radiation fields. And it means you have a natural identification between the inverse wave operators and the trace operators. It's not simply analogies, they're not simply analogous. There is a canonical identification between the two. So something I said I was going to talk about as well in very brief terms is the Lax-Phillips theory. So it's not a time-dependent approach. It's more a stationary approach through a type of Fourier transform, a plane wave decomposition really of scattering for the wave equation. So it's an analytic theory for the wave equation on Minkowski spacetime with an obstacle. So I'm going to neglect the obstacle. So it's as a result, it's a trivial theory, but that doesn't stop me. And there's still some important features to understand there. And so the method is to construct something called a translation representer for finite energy solutions to the wave equation. So I'm not going to describe this in detail, but so you have a function. So take some finite energy initial data for the Hamiltonian form of your equation, so wave equation on Minkowski spacetime. You associate some function to it. That's called a translation representer. We'll see why. And it's a function of a real variable and a variable on the two-sphere. Okay? If you take, instead of the initial data, you take the solution at time t, and you do the same construction, then you're going to associate the same translation representer, but translated backwards in time by the value t. So that's why it's called a translation representer. Okay? So it's a sort of classic spectral construction. The idea is that you diagonalize the Hamiltonian for the equation, but you do it on infinite energy things. But it's not. It's a sort of standard thing, and you reinterpret. Then they reinterpret. So Lax and Phillips reinterpret K as the radiation field for the solution. So that's what showed Friedlander how to do the conformal scattering in the first place. And so what does this mean? It means that if you look at the solution, so its two components are phi hat and dt phi hat, then K, the translation representer, I'm sorry, really is the limit of dt phi hat along an outgoing null geodesic. So you might be surprised by the fact that there's no R. Remember that phi hat is already rescaled, okay? And, okay, so now we have the three theories. So the question I wanted to address is, can one construction in one approach yield result in another approach? So first of all, if you work on stationary frameworks, then you have a time-like killing vector field. And in most cases, it's going to be tangent to your conformal boundary. Okay, so it's time-like in the interior of your space-time, not always everywhere, but it's going to be tangent to the conformal boundary, in at least infinity. And in that case, what will naturally happen is that the radiation field is going to be a translation representer. Why is that? Because you can understand the propagation as a sort of, so I never know which is passive or active, but let's say it's a passive action of a backwards translation. So propagation, forward propagation in time t, you can understand it as pulling the carpet underneath yourself backwards instead of moving yourself. Okay? And but that, you know the action of that on null infinity, so it's a backward translation along null infinity, or the horizon. So by construction, because of this symmetry, the radiation field is automatically a translation representer. So this is showing that a conformal scattering theory in this type of framework will entail a Lax-Phillips theory. So maybe it won't entail the whole theory, but it will entail a fundamental object, that is the translation representer. So this is what Friedlander did in 1990, and Baez, Siegel, and Zhu later on, 89 and 90. It's not quite the early 90s. On static frameworks, but this is more general to stationary settings. So in some explicit cases, you can show that a time-dependent scattering entails a well-posedness result for the Gauss-Sat problem at the boundary. So this is something that Alain Bachelot did for Maxwell fields on Schwarzschild spacetime, and Dietrich and I did that in 2004 for Dirac fields on Kerr, and other people, Mokhtar did something as well like this. And so these are explicit constructions because these are situations on which you have a lot of symmetries and structure that allow you to do this explicit proof. So only in some explicit cases so far. There's a more general thing, is that a conformal scattering actually does entail a time-dependent scattering result, generally. Okay, so this is something that we proved in 2004 on asymptotically simple spacetimes. I redid a similar construction on Schwarzschild to have a more explicit form due to the principal null geodesics. And so it relies on the fact that the radiation field can be understood as data for a simple comparison dynamics. And so it's the flow along a causal congruence that will allow you to define the conformal boundary. So from any point of the conformal boundary, you have a curve that comes into the spacetime, and this produces a congruence of your spacetime. Not automatically, but you choose it so that it is a congruence of your spacetime, and it identifies all the points of the boundary with points on Cauchy-Hype surfaces. So on Schwarzschild, this is very explicit. This is for Scry, it's the Scry plus, it's the outgoing principal null geodesics, and for the future horizon, it's the ingoing principal null geodesics. On asymptotically simple spacetimes, what you can do is you can consider congruence of null geodesics in a neighborhood of the conformal boundary. So you need to remove a large compact set for each time. And then there's three types of things you can do. You can, first of all, you can consider that these null things, these null curves, are actually complete null geodesics, but not, of course, in the space-time you're considering. So you're extending them in a different space-time. So the ingoing and the outgoing ones, if there are such things, will be extended in different space-times. In this case, they're all ingoing because it's topologically trivial. And so in that case, this would be a situation where you would have an identification operator. Okay, so because your free dynamics or your simplified dynamics does not live on the same space as your full dynamics. But there's other things you can do. You can try to realize your comparison dynamics as living on the same space-time. So you can extend these null curves as time-like curves in the interior of the compact domain. And so you will have a causal congruence. Or you can completely forget about these null curves here and define a time-like congruence in your space-time that ends up at all the points of your conformal boundary, and choose the flow along this congruence as your comparison dynamics. That's all that matters, is that these curves end up at each point at the conformal boundary. And then you get wave operators in the usual manner. So in these two cases, without identification operators, in this case, with identification operators. And then there's the question as the following: does time-dependent scattering entail a conformal scattering theory? So in general, of course, it's no, because time-dependent scattering can be completely very abstract and very general, and you don't necessarily have at your disposal the geometrical ingredients that would even allow you to consider building a conformal scattering theory. You don't necessarily have a compactified spacetime or even a spacetime. But when you have these geometrical ingredients available, then there's two questions you can possibly ask. First one is, can a minimal velocity estimate entail a conformal scattering theory? Second one really is a sort of more precise version of the first one. Can a minimal velocity estimate provide an alternative to stronger decay result? So what do I mean by this? Well, if you remember, when you go back to this case, where you have a singular time-like infinity, okay? So there was the question of proving decay results on this future hyperboloid. So these are very strong results that usually use very, very strongly the local structure of your spacetime, and particularly the structure of the trapping that you're dealing with at the photon sphere. And there's a sort of folklore in scattering theory that local features don't matter. It's only the asymptotics that matter. So using very strongly and fundamentally the local trapping in a compact domain in the bulk is something that is a little frustrating and very technical. So the minimal velocity estimate, on the other hand, is not yet, is something that uses spectral analysis and the asymptotics. So it's in a sense a little more satisfactory for constructing a scattering theory. The problem is that, for one, you're trying to understand decay on a full hyperboloid that you push in the future. For the other, you know decay in a narrow cone. The narrow cone can be as close as you like to a light cone, but not identified with a light cone. Okay? So when you push these two things in the future, they will be a difference. There will be a portion of the hyperboloid that you're not touching. So the question is, can you understand the behavior there through the information in narrow cone that are not uniform in epsilon? Okay. So the hope is that if you have good approximate global conservation laws, then this may be a valid strategy, but it's quite likely that you will have to use other features from the Moore theory, like microlocal velocity estimates that are near the light cone. Of course, if you need to use the whole Moore theory, well, okay, there's not much point. So that's questions for the future. And I will stop here. Thank you very much.